Right, we're now looking at forces, and we've got this rocket here, and if you look at the diagram, there's air resistance acting that way, weight acting that way, direction of the movement upwards. So it says, how does the velocity of the rocket change as the rocket moves upward? Well, if it's moving upwards, it's going to slow down, or the velocity is going to decrease. And the reason is, air resistance and weight are acting against the direction of movement. Another way of phrasing it would be the resultant force is opposite to the direction that the rocket is going. So it's going to decelerate or slow down. And second question, again, really simple one for the end of the paper. The velocity of the rocket is not the same as the speed of the rocket. You've just got to know the difference between velocity and speed. And velocity is speed with direction. So this is where we've referred to 10 metres per second would be speed, but positive 10 metres per second or negative 10 metres per second would be referring to the velocity, because there's your direction. Okay, here, the speed of the rocket is 12 metres per second, the mass is 0.05, calculate the kinetic energy. Dead simple, we're just using the kinetic energy equation. So write your equation down, then put the numbers in. Don't forget that squared sign, which means that that is going to, when we put the numbers into our calculator, become 144, giving us a kinetic energy of, so we've got 3.6 joules of kinetic energy. And the second question, as the rocket moves upwards it gains gravitational potential energy. Now this must come from the kinetic energy we had up here. So state the maximum gravitational potential energy gained by the rocket, ignoring air resistance. 1 mark. You're not going to be asked to do any calculations. That's your hint that, yes, it is right. It's 3.6, because all the kinetic energy turns into gravitational energy. And then we look at the bottom one. Calculate the maximum height that the rocket will reach. Well, we know it's potential energy now. Again, ignoring air resistance, we've got gravitational field strength. So the equation we were looking for is E equals m times g times h. Plonking them all together, the maximum height is worked out after rearranging equations. So we've got 3.6 in there, equals same mass, 0.05, times 10 for gravity, times h. Now we're going to rearrange it to leave h on its own. So we're going to, first of all, simplify it. So 3.6 equals 0.5 times h. Let's just put doing them two together. And now we've got to rearrange it. So we need to leave h on its own, take the 0.5, do the opposite of what it's doing. It's currently doing times, so we're going to divide by 0.5. Cancels that, leaves h. So the maximum height is 7.2 metres. And this question threw a lot of people. As the rocket falls, how does its velocity change from the maximum height? Well, everything we've talked about falling is at a graph of that shape. So very fast speed as it falls, but then as air resistance increases as it goes downwards, so acceleration decreases until it falls at a steady speed. Okay, and this final question. Fairly straightforward really, but let's just underline the key ideas. What pattern links the angle at which the rocket is launched and the range? So we're just looking at angle and range. So let's be systematic and start with a small angle. So start with 20 degrees. It's 20, the range is over here. Increasing the angle, the range seems to increase. Increasing to 45, it increases again. So it seems to be that as the angle increases, the range gets further. But then we increase again and we go to 60 and the range seems to come back and get smaller, increase that to 70 and it goes back even further again. So the pattern is it increases, the range increases with the angle up until 45 degrees, and after 45 degrees it seems to decrease again. Fairly simple, fairly straightforward, but you've just got to be systematic with how you say it on the paper.